for rotation of the axis of the rotator.
Inertia?
Huh?
Maybe inertia?
Okay, now, even if you are with physics background, do not stay silent. So, rotation. There are toys.
The fidget spinners.
And they do not maintain the axis of rotation as time goes by, right? If you set it up very vertically, it may stay vertical, but if it is at some angle, it will, the rotation of the widget will change with time. And is there a special word to address this effect? If you want to read more in Wikipedia about this, what should you do? Which word should you explore?
Spinning?
Yeah, okay, spinning, but you have heard. I'm not the first one who is telling you about it. Well, I'm just repeating the same what London did. So change of the axis of rotation is known as, first letter is P.
Precession?
Yes. Okay, so in rotations, the all three directions interact to each other. It's a summer. That so feel free to play more.
You should. Just a lot of fun.
It's just a big fidget spinner.
Just don't hit anyone in the face.
It's kind of hard to do while sitting.
Yeah. So we have only 8 meetings left, right? My plan was to make the doodle pool, but then I decided we can face each other. Anyone who is not able to stay 2 hours on the last Friday in 2 weeks from now? 1, 2.
Stay 2 hours past the class?
No, stay 1 hour past the class.
I can do maybe like half an hour.
But you have something right away.
No.
If it is only one person, you can just present first and depart. Because I do not want you guys, so I want me to come at the assigned exam time, 8 a.m. on Wednesday. So I think I'm getting your support and approval for making this stuff. So maybe we can come in time, especially, and try to be quick and energetic, but there should be time between talks for questions. I know that by practice that you can do short presentations one after another, but naturally there will be questions and wish to discuss something. Okay, so if nothing bad happens, we'll plan on meeting 8 times and avoid exam week. I do have all homeworks and grades. If you didn't hear from me, it means your grades are fine, and it's just issue of formally returning, but you are progressing well. There will be time for you grading me. Probably it will be administered not in paper but electronically, so please do not avoid it. Even if you have some negative concerns, it's much better than doing nothing. So no comments means lowest possible grade for me. Fine. So when you see invitation to grade the instructor, follow it. Even if it is not perfect, it needs to be done. Where we are in the course. Of course, this is too ambitious. In the remaining 8 meetings, we do have 2 labs. So we have only 6 meetings in class time. And out of them, also 3 will be used for the project. So next time, Wednesday, I will explain in details how to prepare written reports, what to include, what not to include, what are criteria of success. On Friday this week, you all will bring 4 pages reports on your projects, which the data will be completed during the Wednesday night. And on Friday, we will do going over this written projects together. Okay? Then on the last week, there will be only 2 meetings for new class material, and the very first and second, and the very last meeting will be presentations. So in fact, we have only 3 meetings with new class material. Although I have ambitious plans for about 10 meetings. But maybe next year, squeezing stuff that was at the beginning and doing more extensively. But I hope you did, well, we are not done yet, but you were enjoying the class as we go and appreciate the focusing more on slow building of fundamental and leaving the technical details for the future, because without background there is no reason to go to advanced subjects. So, projects. I think we are clear on them, and it is not yet late. Even if you didn't start doing anything, Wednesday night is sufficient to complete the project, generate all data. So where we are in the material. Right now we are looking on the rotational motion, and again, we are not going too much ambitious in the subject. So rotation, Harvey linear motion, so not linear, and instead of typical basic variables of position and momentum, we may design new independent coordinates and new operators. One of them is rotation along the z-axis, and we did start with 2-dimensional rotation, which means for this wheel, we nail down the axis and allow it only to rotate left or right. So it's a little much less ambitious. It is very poor kind of motion, not as exciting as 3-dimensional precession, but still useful to get through in the mathematical sense. So amount of motion for rotational motion is angular momentum, and it can be formulated as derivative in respect to the azimuthal angle. And then the eigenstates, well, our goal in any direction, in any application, in any system is to predict future. But before going to this, it is very helpful to solve time-independent Schrödinger equation, find eigenstates, and use them as a basis, if it is possible, and just get some insights about the states. So for 2-dimensional rotator, eigenstates are analog of plane waves with discrete spectrum of this, how to say, analog of momentum. Rate how the phase increment along the motion over the circle threads. So there are rotations forwards and backwards, discrete. And the z projection of angular momentum and total kinetic energy of rotational motion, these 2 operators commute. Therefore, we did found eigenstates of the z projection of angular momentum and plugged in these states into Hamiltonian to find the energies of rotation. So rotating forwards, backwards, energy goes as parabola, which is very similar to what in a square box? Oh, particle in what? Right? So, and for there is an effect of degeneracy. If you do have rotation forwards and backwards with the same pace, it gives the same energy. So rotation forwards and backwards gives same kinetic energy. What else? Looking forward, there will be no class in time to go over 3D rotational motion in such details as we went through box and harmonic oscillator. But this is an exciting area, and if you would solve everything carefully for three-dimensional motion of either electron nuclei or diatomic molecule rotating, their eigenstates depend on two quantum numbers. One corresponds to total kinetic energy of rotation, and another is projection on z-axis. And the projection on z-axis does not change total energy, and in three-dimensional rotations, in contrast to two-dimensional, there are additional states allowed in between this line. So in two-dimensional it is only left and right, and in three-dimensional there are additional states which are also degenerate. So same amount of kinetic energy, but different projection of the z motion. Maybe it's not possible to do anything at the end. It's better to do now. So suppose that I'm a robot that can spin it with the same velocity at each experiment. One kinetic energy, and if it rotates in x and y, then z goes here, z projection. Now I'm rotating it with the same velocity. But z projection, if we average over this motion, or this precession, then projection onto z direction will be infinitesimal, very small. And I can set it up at different angles. So you see that total kinetic energy is the same, but z projection is different. So you do not need to be quantum to see this. And energy goes not literally quadratically, but like quadratically plus linear. These non-new materials, still going over previous things. So one can tabulate, and if you would have time, you would make also the density of states. So for this orbital quantum number, there is a degeneracy. So how many states have the same energy but different projections on z, and it grows linearly. 1, 3, 5, 7, right? 2l plus 1. And the energy can be expressed in terms of kinetic energy divided by all elementary constants, so it will be dimensionless. And then the energy will go kind of quadratically, 0, 2, 6, 12. And the offset between nearest energies will grow linearly. So this linear growth of the offset is important in which spectroscopy? Okay. This linear offset is important in rotational what? Spectroscopy. So if you do have interatomic vibrations in diatomic molecule. It can stay in the zero vibrations or first excited vibration. But this molecule rotates as well. And there are rotational substates here and there. And if we are talking on the low frequency infrared, just infrared, we can induce infrared transitions, not only from the red line to red line, but also between these rotational sublevels. Why? Because everything, or most of things in the world, occur not at 0 K temperature, but at elevated temperature. And if you raise the temperature, the levels that are of the not very high levels of small offset from ground state are getting populated by Boltzmann, right? So these states which are very close to ground state are populated. Therefore, one can make a transfer from one to another there, right? So it is what happens in the rotation plus vibration spectroscopy. So these transitions are affected by several effects. So first, it is approximately equal to the offset of vibrational level. Second, there is, I'm going to make an overview. It's not in our time range to go over the details. The intensity, the probability of transition can be computed through our concept of matrix elements. So you set up initial state, final state, and operator of interaction, which would resemble the electromagnetic field, how it acts on a molecule. And then there will be balance between occupations and resonance condition. We are done with theoretical spectroscopy. So the resonance condition would compose of the light frequency, the delta, let's put this H omega vibrational, and then offset between vibrational states with different L, with different amount of vibrational motion. Occupation comes from Boltzmann. And this matrix element can be taken with sufficient time. But what is important here, if one carefully takes it, it will show a delta function, one of our new friends, that connect initial and final states that are offset by 1. So here this thing will be delta L initial, comma, L final plus minus 1. So during optically induced transitions between this vibrational and rotational sublevels, the amount of vibrational motion can change, not can, will change by plus or minus 1 quantum of vibration. So not any vibrational state can be promoted to by this optical transition. Therefore, when one performs this thing and explores it as a function of frequency, one is getting, oh, it's enough, images like this. So it like a bird with 2 wings, right? And the center, which is typically 0, would correspond to 0 to 0 transition. And there is nothing, because violates the selection rules. So this delta function on the previous slide, this is selection rules. This matrix elements is getting selection rules. And then, if one goes from 0 to first, 0 to second, 0 to third, they all are offset by amount of energy that grows linearly. And then it grows, the intensity grows because degeneracy is increasing as far as we go to higher and higher states. But then, if we are going to higher energies, the intensity decreases because of higher energy states are not occupied by Boltzmann. Okay, today it was an example of traditional P-Chem course for undergraduate. It should be year-round this way. But we are trying to do a little bit more. Yeah, Boltzmann, population, so we're kind of aware of vibrational spectroscopy. Okay, new material. What is angular momentum? By now, what is your impression? How would you? We already have an agreement of presentations, no exams and no more homeworks. The only homework will be written reports on the project. But if you would have a surprise quiz or an exam with verbal question, what is angular momentum? How would you try to answer it? Let's discuss. Like you are walking through the store and suddenly a stranger. Okay, help me. I need to know what is angular momentum. Well, it's not a very practical situation, but what if you are in a mood to answer? What would you answer? Andrew?
My guess would be mass times angular moment or velocity.
Okay, yes. This is simple mathematical expression for two-dimensional rotation. But one can go either, thank you, go into more detailed, more general mathematical definition, or one can go into very philosophical definition without any equation. So, metaphysics, close to philosophy, close to non-mathematical definitions. So, what is angular momentum? How would you explain it?
You're taking the course.
It's like the tendency, it basically tells you how hard it would be to get something to stop rotating.
Okay, yes, yes. So it is analog of linear momentum, right? Which is measure of motion, so quantity of motion. Linear momentum is quantity of linear motion. Angular momentum is quantity of angular motion, rotational motion. And then the rest are boring mathematical details. No objections. Quantity of motion. But you have seen that this rotational motion can be complicated and involve all directions. So it can, the axis of rotation can change. So it can simultaneously rotate around several directions. We are lucky. We can make errors and we will stay alive in spite of the errors if you do some this angular motion and angles. But if you would be pilots, we would have less chance for errors because they need to tune in all three axes. So there are professions who need these rotations critically. So an object can rotate in different planes, and if it rotates in one plane, we can assign a vector in the direction orthogonal to this plane as a measure of rotation. So like if it is circular motion, vector r from origin, vector p for instantaneous linear momentum, and then one can make a cross product, which means the vector equals to the their absolute values and oriented by 90 degrees to both of these vectors, right? How do we rephrase this definition and this concept of the vector of angular momentum perpendicular to plane of rotation for three-dimensional rotations? Basically, this is nothing more than asking how good you recall the definition of cross product from whatever calculus, linear algebra, and analytical geometry. I know what I will do. Please give me a sign if you do remember what is cross product. Huh, okay, I'm not asking the second question because I see. I'm just lazy to ask someone to come and help me. I'll do it myself because I have a backup slide. So, please, then if you know what it is, you can correct. So, we have two vectors, r, which is x, y, and z, and p, which is px, py, pz, right? And then we have the result of their cross multiplication, which will be Lx, Ly, Lz. So basically, we need an expression for each of these projections. Please give me a sign if you do remember how to compose these projections. Please give me a sign if you cannot remember. Okay, good. So a little more of the concept. So right now, in 21st century, and actually in 20th century, we like to store vectors as just a column of numbers, right? At the end of 19th century, in Great Britain, British scientists liked the, I don't know this word, but like basic vectors, wrapper vectors, unit length vectors that determine the direction. So instead of storing vectors in this form, they were assuming that there is an elementary vector in x, which is abbreviated as I with vector. There is elementary vector in y of length 1, which is letter j with vector, and there is a elementary vector in direction z, which is letter k with symbol vector. So it's like 3 vectors of unit length, so that they all are orthogonal. And then one can record any vector, for example, our r vector, as projection on direction x times a vector that is oriented along x but has unit length, plus r projection on y times a vector that has unit length and is oriented along x and y, plus let's see what is there, plus r sub z times k. Okay? Makes sense? So, and there is a convention that helps to memorize and abbreviate the cross product, and in fact it will result in the same spatial orientation of the vectors involved in the cross product. So it is based on this notation, and it is you construct 3x3 matrix. Give me a sign if it is boring and you knew it from the kindergarten. I withdraw the word boring. It's definitely boring, but let me know if it is not new, or you do not like this recall. Okay, I see some signs, but not from everyone. And I would agree that it is boring. So you compose 3x3 matrix. In the first row, you put this symbolic vectors. In the second row, you put projections of the position vector. So distance from the origin to a point on this view. And the third row is instantaneous projection of the linear momentum. 3 projections, x, y, and z. And then if you take determinant, then you will get a vector that is oriented according to our R times P rule. Okay? How do we practice? I'm sure you all know what is determinant. Let me just check it. Give me a little sign if you would not be able to take this determinant easily. So everyone can do it, right? I can do it. So you take the first element and multiply it by algebraic complement, by the things that are left after crossing out the row and column of this first element, right? This times this algebraic complement, and then the rest for the whole first row with alternating sign, plus, minus, plus, and if it will be bigger dimensions, it will keep alternating. And for this algebraic complement, you just do product of diagonal minus product of diagonal, right? So whatever comes here will develop projection on x. Whatever comes here will develop projection on y. Whatever comes here will develop projection on z. And, well, before we flip to the next page, so for projection of x, it will be y times pz minus z times py, right? So it involves, there is no letter x here. So or maybe it's more natural to speak about this one. So for rotation that is described by projection z, you involve position and momentum in the x and y plane. Okay. So projection on the motion in x and y, and projection on the position on x and y. So x, py, x, y. And when we were speaking about linear motion, we always were discussing products of position and momentum along the same direction. Actually, we always had the same direction. It was x times px minus px times x. Here we have this x and momentum in different direction. just interesting to observe. And we can recall back what we did in previous part of the class and replace px, py, pz by the quantum definition of derivative along the appropriate dimension. And then we have the three components, and each of them is differential operator involving derivative over all but these variables. And the signs are alternating. Do not worry, we are not going to go into much details this year. Maybe next year there will be some homework on this, but you're safe. Now, what do we typically do before going into the diagonalization, eigenstates, and predicting future? What we were doing after introducing operators in the past? Or like last thing, almost last thing that we did with creation and annihilation operators.
See if they can.
See if they commute. First thing after we introduced position and momentum operators, we also checked if they commute. And the inspection, if the operators commute or not commute, means making a little mathematical experiment. So writing two operators that are subject to this inspection in one order, then swap the order and apply it to the same function and see what happens. You will forgive me if I'm not repeating this exercise. But if we carefully do it, there will be a very important conclusion that forms a basis for all second half of quantum theory, for any kind of three-dimensional rotational motion, for nuclear magnetic resonance, for electronic paramagnetic resonance, and anything that involves rotation. The quantum operators of rotation along x and y do not commute. Their commutator is not equal. And it is not equal to constant. It is equal to quantum operator of rotation along z-axis. So in a little bit simplified common language term, it means that if, I wouldn't make it on me as an example, if you rotate something in x dimension and y dimension, and then rotate it back, y and x, as a result, it will rotate around z direction. This can be practiced. Well, I did practice this. If you know, there are tools to draw molecules or atomistic model, and some of you are already exposed to this. So you click with three-dimensional model, and then you can rotate it. And it is, when you start it, it throws you off because you need to have three-dimensional vision. But if it is difficult to rotate it at once along a given axis, you can do little going up and down, up and left and right in one dimension, and making it up and left, and then it will rotate along all three dimensions. So the rotations in two dimensions are not independent. They will result in the rotation in the third dimension. And the same thing would apply for all of these operators. Like if you put here x, z, zx, there will be y here. If you put z and y, z here, it will give x. So all rotations are connected to each other. They're not independent. from the common sense, and for quantum operators, it is a useful property that eventually makes life of those who want to describe them mathematically easier. And I want to surprise you, but there are also creation and annihilation operators for rotation motion. But there is no time in the course to cover. So, what else? This is shorthand notation. We remove the function and we just write the commutation for operators. So, elementary preliminary step for any description is to find eigenstates, which is just Hamiltonian times wave function equals eigenenergy times wave function. What is Hamiltonian for three-dimensional rotation? Since it is a kinetic energy, and angular momentum squared is a measure of kinetic energy for rotations, it is this angular momentum squared over 2I, where I is a measure of inertia. So mass times distance from origin squared. And it can be composed as sum of the squares of three components. This is correct, and this can be practiced if one would like, for example, to modify the wave propagation code in 3 dimensions and write numerical solutions. But analytically, it is a dead end. It is too complicated. This orthogonal 3-dimensional Cartesian projections for rotational motion is a keyword. So the only way to survive is to set up new system of coordinates where one does set up the azimuthal angle and the body angle. And if the distance from origin stays, absolute value of distance stays constant, then instead of 3 coordinates, we will have only 2. So wave function is defined as probability amplitude on a globe. So distance from center to surface is constant, but then there are mountains, ridges, and some profile on the surface. This is rotational wave function. And there is another trick similar to the one that we did for 3-dimensional oscillator. We did identify that for, not oscillator, 3-dimensional box, motion in each of 3 directions were independent. Therefore, we were able to separate variables. So there is a similar trick possible for rotational motion where the wave function depends on product of 2 lower level functions, each of which depends on either azimuthal angle or body angle. And since there are 2 independent variables, there are 2 quantum numbers. So the wave function, the part of wave function depends on azimuthal angle is just, you don't see here, exponential to the power I quantum number phi. And this one is spherical harmonics that are a little bit challenging for the given time. But if you take the spherical harmonics for given quantum numbers and take their real and imaginary parts, it will be for the set of atomic orbitals that you probably know from kindergarten. S orbital for angular momentum 0, P orbital for angular momentum 1, and then D, F orbitals. It's probably would be a good thing for me to draw them. What is next? What are plans for the remaining? For the next 2 lectures, which will be only on next Monday. So for provided total angular momentum L, the magnetic projections are less by absolute value, and there is a way to set up a vector of angular momentum which will take different angles, and this will span over all possible quantum numbers. After we are done with review of this opportunity, we will make an analogy between angular motion and spin degree of freedom, which is rotation, analog of rotation that is able to go forward and backwards, but only with one value of angular momentum, plus 1/2 or minus 1/2. So it doesn't span over all values. Meeting is done. Where's my favorite slide? Yes. Looking forward to see you on Wednesday. Okay. So this subject doesn't scare you, or you don't know that it should scare you.
I'm more about to be.